Kinetic molecular theory. We talked way at the beginning of the semester about the difference between a theory and a law. A law says what happens, a theory explains why. Okay, we've been talking about gas laws. They say if the pressure doubles, the volume goes in half. It says what happens. This is what explains why these things happen. It's the simplest model. Kinetic, meaning motion of molecules. A theory about the motion of gas molecules. So we look at a gas as a collection of particles. They could be molecules or atoms, depending on what the gas is. They are in constant motion. Since we're here, let's just look at, these are not lines, these are molecules moving, and they've got these little lines like a cartoon that they're moving. And they're going to go in a straight line until they run into something, and here's two that collided and they bounced off of each other. So that's the motion of gases. I think you're all too young to have actually played this when you were children, but maybe you've heard of an old ancient video game called Pong. You heard of Pong? It's a black screen, this white line at the bottom that just moved right and left, and this little white blip. And the blip would move in a straight line until it ran into a wall or it ran into your pedal. And the idea was just to keep it moving. That's how I envision gas molecules. They're like a Pong game. They're just going to go straight until they run into something. It's important to understand that the size of a gas particle is negligibly small. Now, obviously, a gas particle does have mass. It does. But we can assume in this theory that the gas particle occupies zero volume because the volume is so small compared to the volume of the whole gas. There's just a lot of empty space. Here's an example. At STP, argon atoms occupy only 0.01% of the gas volume. So the volume they take up, only 0.01% is the actual molecules, atoms themselves. So if the argon atom was the size of a golf ball, its nearest neighbor would be 4 feet away. So golf ball, 4 feet. There's a lot of empty space. Average kinetic energy is measured by temperature. Temperature is a measure of the average kinetic energy of a substance. So here we have these gas particles, they're moving. Their average kinetic energy is directly proportional to the temperature in kelvins. Because you can't have negative kinetic energy, can you? No. And at 0 Kelvin, what would happen to the motion of the gas particles? They would stop. Because 0 Kelvin would be 0 kinetic energy. The only way to have 0 kinetic energy is to not move at all. What's important to note is we're talking about an average, but not all the gas particles are moving at the same speed. Some are moving faster and some are moving slower. The temperature just measures the average speed. When a particle collides with another particle or with a wall, the collision is completely elastic, and that's a physics term. An elastic collision means that no energy is lost when the two things collide. On that Pong game, the little, was it called Pong? Yeah. The little blip, was that a Pong? I mean, it was supposed to represent a ball. I'm going to call it a blip. The little blip, sometimes you could get it stuck, right, so that it would bounce around and you didn't have to move the paddle, and it would just go forever, right? Because it was electronic, it didn't have to obey the laws of physics or anything. It would just keep going, and it would keep colliding with the walls, and it wouldn't lose any energy. Now, in real life, in things that are large enough to see, probably the closest thing in everyday life we have to it would be playing billiards. And so, you know, you've got this nice smooth surface and these relatively heavy smooth balls, and so they have limited amount of friction. You hit a pool ball, and it's going to roll and run into other balls, and it's going to have a fairly elastic collision with the other balls. But gas particles have completely elastic collisions. So they move and they bounce off, and they don't slow down over time like larger objects do. So there's no overall loss of energy. They can exchange energy. You could have one run into another one and have the one lose energy, but the other one would gain an equal amount, and so the total energy is maintained. Oh yeah, see, I get ahead of myself all the time. I don't know what's coming up. So here's the example of these two pool balls colliding, and the force, I guess they're coming this way. Actually, there's an arrow there. They came this way, and the force is transferred, and they're going off in different directions, but they're still moving. This is an example of an inelastic collision. If you take two balls of clay and roll them at each other, they'll just go boom and stop. They are soft, and they will absorb the energy of the collision instead of transferring it to the other object. So this helps us to understand the nature of pressure. The gas particles are constantly moving, and they're striking the walls of the container. They're striking with force. Each of those collisions is very, very small, but we have a lot of them colliding. And so that gives rise to the pressure of the gas. It's the force of those collisions divided by the area over which they're colliding. So we can explain some of these simple gas laws. Boyle's law says the volume of a gas is inversely proportional to the pressure. So if we think about decreasing the volume, so here we've got one cylinder of gas, and we're going to cut the volume in half. What's going to happen to the number of collisions? They're going to increase. It's a smaller container. They're going to run into the walls more frequently. That's going to cause the pressure to go up. Charles' law says that the volume of a gas is directly proportional to the absolute temperature. While kinetic molecular theory says if we increase the temperature, the average speed and thus the average kinetic energy of the particles increases. That greater volume is going to spread out the collisions over a greater surface area so that the pressure is unchanged. In order to keep the pressure constant, which Charles' law relates volume and temperature at constant pressure, if you increase the temperature, you have to spread the gas out in order to maintain the same pressure, so the volume will increase. Avogadro's law. Volume is proportional to the number of gas molecules. You put more gas molecules in, then more are going to hit the wall. In order to keep the pressure constant, you're going to have to increase the volume. So if you think about gas particles, like the blip in the Pong game, and think about what happens when it hits the wall, that's exerting a force, and force divided by area is the pressure. If you increase the temperature, the particles move faster. You can logically think out all these gas law relationships. Dalton's law. The total pressure of a gas mixture is the sum of the partial pressures. Well, kinetic molecular theory says the particles have negligible size and they don't interact with each other. Particles of different masses have the same average kinetic energy at a given temperature. And because the average kinetic energy is the same, the total pressure of the collisions is the same. A heavy gas is going to be moving more slowly to have the same kinetic energy, but the kinetic energy of the different gases will be the same. So the kinetic molecular theory is a quantitative model, and it implies the ideal gas law, PV equals nRT. So let's see if we can follow this. The pressure on a wall of a container occupied by particles in constant motion is the total force on the wall due to the collisions divided by the area of the wall. So here we have this container, And we've got gas particles in here. The pressure is the force divided by the area. So the force, well, I think this is coming up on the next one. Newton's second law tells us that the force of a collision is the mass of the particle times the acceleration due to the change in direction. For each collision, the acceleration is change in velocity divided by the time interval. And the change in velocity is 2 times the velocity, because the velocity before was v, going in one direction, and now it's going minus v. So the change in velocity is 2v. I think I'm supposed to write some equations in here. Let's see if I can remember them. So the force of a collision is the mass of the particle times the acceleration. And acceleration is the change in velocity divided by a time interval. That change in velocity is 2v. So the acceleration is 2 times the velocity divided by the change in time. So if we plug that into this guy, we have force equals mass times 2v over the change in time. The number of collisions in that time interval on an area A is proportional to the number of particles that can reach the wall in that time interval. So if we're looking at this wall back here, it has an area that we're calling A. The number of particles that could possibly hit it during that time are all the particles within velocity times that change in time. This time interval and this distance. So those particles occupy a volume of velocity delta t times A. And the number of particles is equal to this volume. What? The number of particles is equal to this volume. Gosh, I hate it when I do that. N over V. Density, I lost it. Oh, this is so cool. It's a shame that I screwed it up here. The ideal gas law just comes out of it like magic. Pause. Well, let's see if that goes anywhere. The volume that the particles occupy is the velocity times the change in time times that area. The number of collisions is going to be the volume. No, I just completely screwed it up. Okay, so I did this summer, so you can go back to that video and watch that one.